Okay, in this video we go over the inventory homework solutions. The first problem is an ABC classification, and what we're needing to do is determine what the most important items are and are least important. And for this example, or for what from the book, is we evaluate value based on taking the unit cost multiplied by the usage. So here is the data in Excel. And the first thing I did was take the product of the usage of the unit cost. And once I've done that, I'm going to take it and I'm going to sort by my unit cost times usage from big to small. And now I can look at item 8 is my most important, item 16 is my least important. How do I determine the breakdown? I'm going to sum my total unit cost value and determine what proportion is each of these, and then build a cumulative. So this is the percentage, and this is the cumulative percentage. So you can see that your A items are usually about your 60%, top 60%, so I would probably call those A items. Your C items are generally about the final 10 or 15%, so I would probably call those C, and somewhere in the middle B. So I would A, B, 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 and I think C and the rest of them. And that's a little bit arbitrary. You're cut off on between what is an A and a B, maybe slightly different than mine. And the most important thing is that item 8 is a very important item. How you manage that, who you purchase that from, is very different. You should manage that very different than item 16, which is not a very important item for you. The next problem is an economic order quantity, and our units of measure are bags, and we're trying to figure out how many we should order when the cost of ordering is $10 for every order. Has no function of how many we order, and the annual carrying cost is $75 per bag. And the annual carrying cost is the cost if we put a bag on the shelf, what it cost us in storage, protection, obsolescence, spoilage, and someone has figured out that it cost us $75 for every bag that we have stored. So given that this is the annual demand, this is the cost of carrying a bag for a year, this is the cost of ordering, so the economic order quantity formula, square root of 2 times D times S over H. What is my average inventory level? It's just this divided by 2. The number of orders per year is your demand divided by the number your order quantity. When you follow the economic order quantity formula, determine your order quantity, then the cost of the holding and the cost of ordering will be exactly the same. That's one check. And so that's your cost of your inventory policy. Keep in mind, that's not the cost of buying the bags at all. That's just the cost of your inventory policy. You don't forget that there is the cost that you're going to have to purchase 1,215 bags, and they cost something. Don't forget that. It's not included in this because that's a cost that you're going to have regardless of how often or how large your order quantities are. There is in the book a more advanced problem where we have price breaks. We're not covering it, but it's not much different than this. And if that's something you have questions about, let me know and I can expand on how to do price breaks. The last part of the problem is, what if our holding cost increased by $9? And to solve this, you need to redo the problem because now your cost drivers have changed. And so when the cost of carrying increases, then you should order less more often. So our order quantity drops and we order more times per year. And now because it is an increase, then there is a penalty, and so the annual carrying cost will go up by 70, or the annual cost of your inventory will go up by $79. Problem 3 is a safety stock and a reorder point. This one I got a lot of questions. So when you read this problem, the lead time is 2 days. So that's a statement, and how you need to interpret when you see that is that the lead time is 2 days all the time. So there is no variability. The lead time is exactly 2 days. So if that's true, then your standard deviation of lead time will be 0. There's no variability. If I said the average lead time was 2 days and the standard deviation was 1 day, well, then you got a standard deviation. But when the statement is lead time is 2 days, that means it's 2 days every time, all the time. It's a constant. So the standard deviation is 0. So once we have that, there's your average demand per week. And this is your standard deviation of demand per week. We have a target service level of 90%, so we can calculate our Z by using the norm INV function. Our lead time, we converted this to weeks, which is 2/7 of a day, with the standard deviation equal to 0. So if you use that long safety stock formula, Z times the square root of everything under that radical, that tells you that the safety stock is 2.4 gallons. So your reorder point is your demand times lead time, the average demand times average lead time, plus your safety stock. So remember, the 2.4 gallons, that is the amount of inventory you carry because of uncertainty. We have uncertainty in our demand. And then our reorder point is that number. And we start with what our average demand times lead time, which is 21 times 0.29. So with no variability, if we didn't have any variability, our reorder point would be 6 gallons. But we do have 2.4 gallons of safety stock because of uncertainty. Now, it's not a great example, but if you look at the lead time, what if that lead time was, we had some. So when we ordered something from someone, what if the lead time was not constant? What if it was 1 day? Oh, that's sorry. If that existed, look what it does to our safety stock. It went up from 2 gallons to 5 gallons. So we are or can benefit from a lead time of nothing. So when you work with your suppliers and can reduce variability, you can reduce the amount of safety stock that you have to carry. And the last problem is a newsboy problem. We are buying fresh fish to sell in our restaurant. After that day, we can't sell it in our restaurant, but we can sell it salvaged to a cat food maker. And we also know that demand, our daily demand, is a normal distribution centered at 80 with the standard deviation of 10. So let's determine the optimal stocking level. Oh, that's all I asked. Yeah, that's so. If we look at that, so here are your cost drivers, and this is from a previous problem, but that's the what it cost us to purchase. This is what we sell it for. This is what we want to sell it for if we don't sell it the day for this price. So we have 2 cost drivers. The cost of being short. The cost of being short is your penalty or your disutility if you don't have enough stuff. So if you run out, then what you lose is $1.50 for every pound you're short. And if you're long, your cost of being in excess, we know we can sell it for $2.40, so the difference between $4.20 and $2.40 is what the cost, And this is one of the rare times when our service level that we should try to achieve is less than 50%. It's only 45%. So what that means is that you're not going to buy a lot. You're not selling it for nearly enough money to expect to have good service. What you should do is plan on running out 45% of the time. So if demand is centered at 80 with the standard deviation of 10, the order quantity is not going to be 80. It's going to be less than that. Now, in reality, if I bought something for $4.20, I wouldn't sell it for $5.70. I would probably sell it for $15.70, $25.70. Now, what's going to happen when I do this? Well, now the dish utility is going to be much higher for running out. So this number is much higher, and it targets a much higher service level, so your order quantity changes. So the optimal order quantity is much higher when your cost of being short is, and usually this is a magnitude more than this one. They're usually not the other way around. Okay, that's enough information to do the homework. Thanks.